Okay, so last time we were discussing, this is where we had left off, we were discussing the vorticity transport equation, and this we had derived for the special case of the Navier-Stokes equation, when we had used the Navier-Stokes equation for an incompressible fluid with constant viscosity, right? So we had used this particular equation, we had used the fact that this body force is of a special type where it can be represented as a gradient of a scalar quantity. And then we had gone ahead and we had used several of these identities in order to, and then took the cross product here in order to arrive at this. Okay, so this is a very important equation, and if we have to interpret what each of these different terms mean, so you have on this side you have the familiar term, which is the total derivative of a quantity. So, and on this side you have an interesting set of, there are two terms, and both these terms sort of look familiar and should look familiar because they are derived from a familiar equation. But this term basically represents the rate of change of the vorticity of the fluid element. Vorticity of a fluid element, which means that we are following a particular fluid element and we are looking at its vorticity and then asking for its rate of change, and that is why it has gone off to, we have to use this particular derivative right here. And here we have, this is a term that indicates the stretching and turning of a vortex line. Okay. So as it goes with the flow, the gradient of the velocity is going to stretch and turn this vortex. Okay. And this third and other important term, this is just like we had the diffusion of momentum, we have the diffusion of vorticity. Okay. Now, interestingly, unlike, so just look at this equation and then let's just go back quickly to look at the Navier-Stokes that we had started off with. You see, there was a body force term, but in the equivalent equation here, there is no body force term. Okay, so that disappears. Okay, the pressure gradient term also disappears. This also term disappears. So this is in a way here because of the special type of body force term we had considered, which is a conservative force field. But if you want to think of it, one way to understand this is that in a uniform density situation, the pressure and the body forces, they act through the center of mass of the element, and thus they cannot produce any rotation. Only shear stresses can produce rotation and hence lead to vorticity. Okay. So, so this is, you can think of it that way. And the vorticity transport equations are quite important because they're sometimes used in numerical calculations in place of the Navier-Stokes equations. Okay. Now, what would happen for a 2D case? Okay. For a 2D flow, this is obviously the vorticity equation, this vector equation is valid for 3 dimensions. But if we look at the special case of 2-dimensional flow, the vorticity equation becomes what? The vorticity equation will become, what will happen to this term? If the flow is 2D, this vector is going to be out of plane, whereas this vector is going to be in the plane. Okay. So this term is not going to exist. So for the 2D flow, you will have this vorticity equation will, transport equation will reduce to this very simple form Okay. So this means that vorticity can only diffuse and not stretch. So maybe I'll just make a note of that. So in 2D flows, vorticity can only diffuse and not stretch. This is such an interesting situation. And what if you have an inviscid flow? Like we had taken the Euler's equation where viscosity was 0. What if that you have that particular case? Then this term is also going to 0. So moreover, if flow is also inviscid, the 2D flow, right, is also inviscid, then this term is equal to 0, which means what? That the vorticity remains constant for each fluid element, right? That's the implication of this. This implies that vorticity, sorry, this didn't come out right. The vorticity remains constant for each fluid element. Okay. In a 2D inviscid flow. So if in a 2D inviscid flow, the flow starts off irrotational, then it must always remain irrotational because the vorticity has to remain constant. This is a very, very important statement. We'll see this a little bit later again. Okay. So these are some of the important consequences. Now I had been holding off on one result that in a sense belonged to the previous chapter, but it is going to be, we'll see why I was holding on to it. So I would like to discuss the Bernoulli's equation, which all of you should be familiar with in some sense. We have discussed one particular version of the Bernoulli's equation before. Now we are going to discuss another version which you're probably more familiar with. So the Euler's equations, okay, which describe the momentum transfer equations for an inviscid flow, they can be simplified to a known expression called Bernoulli's equations. Under certain conditions, okay, so not always, under certain conditions. So we have already started off with an assumption, by the way, that we are dealing with inviscid flow. That's why we said Euler's equations, right? So Bernoulli's under certain conditions, and these conditions are steady flow, steady inviscid flow is number one. Second is conservative body force field, which basically refers to the body force we are going to use. And finally, either along a streamline, and now I will tell you why I have been holding on. Either along a streamline, and till this portion you probably are familiar with this from even in undergraduate classes, or a vortex line. So I don't think this is something that you might have come across in the undergraduate class, that it is true either along a streamline or a vortex line. Okay, and the equation looks like this, and I'll, just like my previous time, I'm going to give you the equation that we are going to reach. So del, okay, this is not P, this is rho, okay, half u u dot u plus g equal to constant. Okay, and this quantity is obviously the same as half this, right? Okay, so let's derive this. So the derivation of this is important. Let's look at how we can justify this. So let us start with the Euler's equations. Okay, so the Euler's equations are the momentum transport equation, sorry, but there is no viscosity, so that term is gone, and then here you have a plus a body force term which we are going to represent as the gradient of a scalar. Okay, so this is basically because this is equal to okay, sorry, I'll just use equal to, that's clearer. This is actually, it stands for that we have assumed that the body force vector is, because it's a conservative force field, it can be represented as the gradient of a scalar quantity. Okay? Because, and that's the definition of a conservative force field. Well, there's another definition, and the conservative force field has a certain consequence, and you probably are already familiar with it. It's conservative force field. The conservative force field is an idea from dynamics, and I think you already know what it is. So we are assuming this particular form once again. Now we know that this breaks up into two terms, and what we are going to do is we are going to expand the second term, okay, which we know is going to be this particular term, right? Okay, this we are going to expand, which is the convective term, and we are just going to expand it using the same identity that we have seen before, which is this. This was the identity minus u cross u. Okay, this is an identity, which means it's always true. Okay, so this, what we are going to do when we break up this term into the two quantities, we are going to replace this term with this equivalent. Okay, so let's do that, and what we find is, okay, sorry, what we now find is that you have on this side you will have del u del t plus del of half u dot u, we'll keep it this way, minus u. We already probably can understand what we are going to do with the term in the bracket, the last term on the left hand side, and on this side you have minus rho del p minus del g, right? Okay, so we have quite a few gradient terms. We have actually 3 gradient terms. So can we club these together? Let us do that. So club all the gradient terms together. I'll just bring all of them to the left hand side. Actually, let me, so I think hopefully you can probably see that we are slowly already coming to this kind of a form, right? So we want to get here, so that is why I brought my pressure term onto this side, and then we are already getting close, and I hope you smelled that. And this is what? This is omega, right? Okay. So now the question is, how do we write this particular term here? Now what happens is, you can write this gradient as the gradient of the integral of dp by rho. Okay. So if you have that, then what you can do is, now I can, so simplifying, we'll take the gradient term, and then let's put all these terms club them into one. This is del p by rho plus half u vector dotted with the u vector plus g, okay, and this is equal to minus del u del t plus u cross omega. Okay, we have come quite far, and now we want to consider special cases, right? So we had started off with Euler's equations, and that's what we have maintained. All we have done is recast Euler's equations till now. We have not introduced any other extra assumption till now. So your first assumption here will be that of steady flow. So this will go. Next, what we want to do is, we rewrite the equations, and then we are going to simplify. So we have gradient integral dp by rho plus half u dot u plus g, and on this side you are now left with only u cross omega, right? So now let us consider the case where we take the dot product with an infinitesimally small line. Okay. So what we are doing here is doing dot product with a infinitesimally small line dx, and let this line be along a streamline or along a vertex line. Okay. Now this vector u cross omega, this is going to be perpendicular to both streamline and vertex line, because it's a cross product. Both streamline and vertex line which implies that this quantity is going to be 0 in either case, right? So we take advantage of the fact that this is a cross product, and that this cross product is a vector such that it is perpendicular to both u and omega, right? That's the definition of a cross product. So once you do that, then what we end up with is, so on this side you have 0, so on this you reduce this side to be 0, so the question is you remain only with this. So you are doing a gradient, okay, and once you're doing a gradient and you're doing a dot product with dx, so this actually just gives rise to an ordinary differential. So this quantity sorry, this is the wrong bracket. this is simply the differential of right, and this quantity is equal to 0, which implies that this quantity del P by rho plus half u dot u plus g is equal to constant. Okay, so we have come to understand Bernoulli's equations for the special case of a steady flow. Steady flow, we began with we began with the idea of inviscid flow, then we impose the condition of steady, and then we impose the condition of we have to take this dot product along either a streamline or vortex line, and in both cases we end up with this equation. Okay, so this is, let's box this. This is a very, very important equation. This is Bernoulli's. Okay, so this is a very important formulation. Now there is one more formulation, and let me just broadly give you that. And that formulation is true for what we call irrotational flow. Right, and irrotational flow implies that this quantity is 0. Right, irrotational is basically the equivalent of stationary. What stationary flow field is to velocity, irrotational is to vorticity. Right, and in an irrotational flow, and we'll see this in the next next chapter, that in irrotational flows, the velocity vector can be represented as a gradient of some scalar. Okay, so this is some scalar function. Okay. And this is easy to see because note that if that is true, then the vorticity, if the flow velocity were to be represented as the gradient of some scalar quantity, then the vorticity, which is nothing but this quantity, is equal to 0 due to the vector identity. Right, so this form automatically satisfies the idea of a irrotational flow. Okay, so in what we had is, if you look at the previous equation, okay, so let us consider the case of inviscid flow, and in the inviscid flow we had said that the equation that we had derived was that just a second, the gradient of, let me collect all the, I was at created all the gradient terms here, which was half u dot u plus g, and this was equal to minus del u del t. okay, plus u cross omega. Okay, so this is where we were. So now consider the irrotational inviscid flow, inviscid and irrotational flow. Okay, so then what we can do is this term goes off to 0, right, and this quantity can now be replaced by the gradient of some scalar quantity. So this equation, what does it become? This equation simply becomes the gradient of del p by rho into half the gradient phi dot gradient phi plus g on this side, and here you have minus del t of the gradient of phi, which is the same as the gradient of, sorry, there's a minus sign, so wait, okay, minus the gradient of del phi del t, right? So if you now, even this has become like a gradient term, right? So we can bring this over here and we can combine all of them. So let's just do that, because we can now combine. So this will become del phi del t, it will become plus if you bring it to the other side, and now you have the integral of dp by rho, okay, and you have half del phi gradient of del phi dot gradient of del phi plus g, okay, and this is equal to 0. Okay, now in this particular case you can take the you can take the dot product of this. So this means that I can, okay, so I'll just copy this equation, I'm not going to, or what I'm going to do is, okay, so we have seen that this is true, right? So this is equal to 0. So if I were to multiply this with some dx element, and now this dx element can be in any direction, okay? This dx direction, that also is equal to 0, which just like last time, what does it imply? Which implies that the derivative of this term this is equal to 0, right? So this, but this time, okay, this is the special derivative, so this quantity now, so del phi by del t dp by rho plus half del phi dot phi plus g is equal to some ft, okay, where ft is some function of time. This is some function of time. Okay, so this is the alternative form of the Bernoulli's equation for irrotational flow of an inviscid fluid in a conservative force field. Okay. This second one is often not seen. You might not have seen this, encountered this in undergraduate classes. So hopefully this time you have seen this, while this is sort of similar to what you might have seen in the undergraduate classes, but this hopefully does take you a little bit ahead compared to what you might have encountered. Okay, now I'll just quickly make two more comments and then we'll move on to the other topic. So how do you evaluate this particular term? Okay. Now remember, this rho is inside. So if fluid is of constant viscosity, constant density, not viscosity, sorry. If the fluid is of constant viscosity, then this integral term dp by rho is simply nothing but 1 by rho integral dp, which is going to be what? P by rho. That would be very simple. But let's say you have an ideal gas. Okay. If fluid is ideal gas, then my pressure and density are not anymore independent. In fact, they are related to each other by the equation of state, which is this. So now here, of course, temperature can also vary. So let us say that temperature is constant. Take isothermal case. Okay. So let us say that my pressure is some rho times R times some T naught. Then what will be my